Hello everyone, my name is Zikai Liu. Today, I'm going to introduce an application of KLEE on education, which is using KLEE as the core of our tools to provide timely feedback.
Zikai, do you want to give the talk live instead?
Yes.
Oh, okay, sure.
Yeah, thank you very much. Yeah, could you see the slides now?
Yes, we can.
Yeah, okay, let's start. And hello everyone, I'm Zikai Liu from ZJU-UIUC Institute. Today I'm going to introduce an application of KLEE on education, which is using KLEE as the core of the tools to provide timely feedback on assembly assignments to students. As some of you might experience in introductory programming classes, there are often many more students than the staff. For instance, in our institute, the ratio of the number of staff to students was more than 1 to 20. Furthermore, at any time of the day, there may be students working on their assignments, while the staff are not available 24/7. This often results in the situation that students are often waiting for feedback, and the staff are often busy answering questions. Why don't we use computers to automate this process? We can use computers to give students fast and focused feedback on their possible mistakes. Our goal is to give specific test cases that cause student code to fail within 5 minutes whenever the student asks for feedback. These days, the common approach is to use autograders with fixed test cases. However, the fixed cases have many drawbacks. As shown in the example, for the code to calculate the absolute value of a number, but with a small mistake of writing a 2 in the conditional checking instead of a 0, the fixed cases shown on the bottom left will not expose the problem. If students submit this kind of wrong code that the fixed test cases cannot expose the problem, they get incorrect feedback from the autograder. Nevertheless, symbolic execution is good at doing these jobs. As shown in the example on the bottom right, the problem in the code can be easily exposed. As a result, we decided to build a feedback toolchain based on the symbolic execution using KLEE. The tools we developed are specifically for the LC3 assembly language, where LC3 is a 16-bit ISA designed for education. Our overall solution can be shown by this graph, which I will introduce in the order of how students use them. Firstly, students edit their code in the VSCode editor with the LC3 extension we developed that produces feedback while students are editing their code. We noticed that VSCode is chosen by many senior students, so we decided to introduce it to the student earlier. After finishing editing, students submit their code through GitHub, as they do in many other classes, which means there are nothing new to the students in this process. After that, our webhook server detects the submission and collects the student code for our main feedback system. Firstly, the regression testing is run to check whether the problems pointed out by the old feedbacks are solved. If not, we will not produce any new feedbacks to the students. This is because some students may make random guesses on changing their code until their score is improved, which is not helpful for them to learn programming. The regression testing forces students to fix the known problems and prevent them from making the guessing game. If the regression testing is passed, the code is then run in the symbolic execution engine for the LC3 assembly language, which we called KLC3. It is built based on KLEE and performs equivalence checking for the student code and the correct version of code. The result of running is written into a report and pushed back to the GitHub server as the feedback to students. Students can see the reports on the GitHub webpage and download the test cases. With those test cases, students can identify and localize the possible problem of their code locally in the LC3 simulator we developed that supports reverse execution using the debugging technique of slicing and backtracking. I'll introduce the main components of our tool in detail. For the VSCode extension, it performs static analysis when students are editing their code and detects common issues. This helps students to fix relatively simple mistakes quickly, and it also helps reducing the pressure on the symbolic execution engine, since students are less likely to submit the code with simple mistakes. Now comes the core of our system, the LC3 symbolic execution engine based on KLEE. As shown in the complicated picture, we built several new modules about KLEE infrastructure. I will walk you through them one by one. Notice that in this picture, the orange arrows represent the data flow of the student code, and the blue arrows represent the data flow of the gold code, which is the code believed to be correct. The first step is the definition of symbolic variables. In KLEE, symbolic variables are defined through some C APIs, but we are developing tools for assembly languages, and there are no such assembly APIs. Instead, we use the comments in the assembly code to specify the input, so that core staff that are not familiar with KLEE can also make use of the tool easily. As shown on the bottom of the slide, the BLKW specified a certain range of memory in LC3 assembly language, and the comments on the right defined those memory locations as symbolic variables with initial constraints. We support both the numerical constraints and some macro that define constraints for string variables, such as the fixed length string shown in the picture. The constraint encodes are handled by our parser we developed. After that, the code and the symbolic variables are passed to the LC3 symbolic executor with our new memory model. During the execution, our executor detects execution issues of the student code, such as accessing uninitialized memory, and those issues are collected for later feedback generations. The code then goes to the process of equivalence checking. In the equivalence checking, the student code and the gold code are run in logical machine that are initially equivalent, while the final constraints of one of them is used as input to the other. In the example shown in the picture, the student code is run first symbolically, producing a set of student paths with constraints on the symbolic variables. The path with execution errors terminates the running, while the constraints of other paths are used as input to run the gold code symbolically. To determine whether the gold code and the student codes are equivalent in the scenario of assignment, one or more of the contents of display, memory, and registers are compared. What to compare can be chosen by user as input to our system, and user don't need to write additional code for the equivalence checking. The equivalence checking produces a set of behavioral issues, which are collected with the execution issues generated earlier. Each of the issues is associated with a set of concrete values of the symbolic variables that can be used to expose the issue. As shown on the bottom of the slides, the example of the issues of student code includes using uninitialized registers, accessing unspecified memory, and producing different output from Go code. However, in real cases, the same execution issues may be triggered for hundreds of times, since each state in the symbolic execution may trigger the issues. As a result, we decided to filter the issues by keeping one of the same type of issues at the same location, since they are likely to be caused by the same problem. However, this is still not enough. Our users are students that are not familiar with programming. We need more human-readable reports for them. As a result, we formatted the issue and generated the reports in a markdown format so that students can look at them in the browser interface of GitHub. This is one example of the feedback given to students. On the left is the report that students can see on the GitHub webpage. It shows that the student code has behavioral issues, which is producing different output than the gold code for certain test cases. The bottom left shows several execution issues of the student code, including using uninitialized registers and accessing unspecified memory. We also give students the specific test cases that can be used to recreate the issues, such as the one shown on the right. The bottom right is an LC3 simulator script that students can use to load the test cases with the code. With the test cases and the simulator script we provided, students then debug locally with the LC3 simulator that supports reverse execution. The debuggers that support reverse execution can reverse the execution effect of the instructions and recreate the machine states in earlier execution flow of the code. It is useful for students since the debugging technique of slicing and backtracking relies on certain earlier machine states. We added such support in the simulator as a part of our tool chain. These are the overall flow of our tool for timely feedback. Let's look at its performance. Our system was used in fall 2020 semester for our introductory programming class. In our most complicated assignment that students write median 700 lines of code, we used an overly restricted input space since our tool was not fast enough at that time. As shown in the orange statistics of the figure, there are a number of samples that exceeded our 5 minutes feedback target. However, still, 80% of the students who took the anonymous survey gave positive feedback on our tool. After fall 2020, we make significant optimization on our tool. The running time of the same set of samples on the same input space is shown by the blue statistic of the picture. All the samples finished running within 1 minute. We also try larger tool on much bigger input space. The green statistic in the bottom figure shows the running time of the same set of the sample with the new input space. Only 4.08% of the samples reached the 5 minutes target of 5 minutes timeout. And all the timeout cases reported some issues, which means all the students have something to work with within 5 minutes. As a result, we think we reach our goal of providing timely feedback. And we think our tool is a good application of KLEE that teaches people how to program. This is all my presentation. Thank you very much for listening.